battle for technological supremacy is often understood through visible products like smartphones, electric vehicles, and solar panels. But beneath these lies technical standards, determining how billions of devices communicate and data flows across borders. The contest over 6G wireless technology is a culmination of strategic positioning, long before Western policymakers understood. While American discourse focused on security threats in 4G and 5G, China was building institutional capacity and influence. Huawei established its first 6G research center in Ottawa in 2017, publishing white papers for future networks. By 2018, Chinese universities and state institutes coordinated programs linking telecom, AI, and satellite integration. This was a multi-decade plan to position China at the center of standard-setting bodies and patent pools. The objective: control over technical standards to gain advantages across every sector dependent on wireless connectivity. China learned from earlier tech cycles. In 3G, they were licensees, paying royalties to Western patent holders. By 4G, Chinese companies contributed significantly to international standards, holding patents and manufacturing equipment. 5G saw Chinese companies achieve parity with Western competitors in patents and deployment. But parity was not the goal. 6G research aimed for structural advantage, shaping the fundamental technical architecture of global systems. This required simultaneous advancement across multiple domains: patent portfolios, manufacturing, and stable research funding. Coordination mechanisms aligned these efforts toward shared technical objectives, not fragmented commercial interests. The Chinese institutional model delivered this coordination. The Ministry of Industry established roadmaps. Universities received sustained funding for long-term research, eliminating pressure for short-term returns. Companies like Huawei maintained research budgets, treating standards development as infrastructure investment. This ecosystem absorbed uncertainty, knowing coordinated implementation would follow once specifications matured. By 2020, Chinese institutions filed thousands of patent applications covering essential 6G technologies. These patents address terahertz, spectrum, satellite terrestrial integration, and AI-native network architecture. They represented deliberate positioning within the standards-setting process, establishing negotiating leverage. Control over standards at the development stage translates into structural advantage across the entire technology life. The United States faced different institutional constraints. Companies respond to shareholder expectations and quarterly earnings. Long-term research competes for funding against stock buybacks, dividends, and clearer near-term returns. This results in systematic underinvestment in early-stage research, especially where technical standards are undefined. No institutional mechanism can commit 15-year research budgets, immune to political and market changes. The consequences became visible in international standards bodies, where 6G specifications began taking shape. China submitted more technical proposals, filed more patents, and sent larger delegations than the US and Europe combined. American research excellence without coordinated institutional backing cannot translate into standards influence. The fragmented structure of American telecommunications meant independent strategies and competition. No mechanism aligned companies toward shared standards objectives, even if it strengthened collective positioning. Meanwhile, national security framing dominated American discourse about Chinese telecommunications. The U.S. government pursued an aggressive campaign to exclude Huawei equipment from allied networks. Minimal resources flowed toward building domestic manufacturing or funding American alternatives to Chinese technology. The political system generated consensus around threat narratives, more isolated than sustained industrial policy programs. This asymmetry reflected deeper structural patterns. Threat framing generates bipartisan political support. Industrial policy requires sustained appropriations, coordination, and patience for programs that may not produce visible results. The result: a policy approach that made Chinese market access difficult, but did little to strengthen American capabilities. Huawei was excluded from some markets, but its research programs continued. Its patent portfolio expanded. Chinese universities trained thousands of engineers. American universities produced excellent research. The graduates often joined software and internet services, reflecting labor market incentives. The manufacturing ecosystem dimension further compounded these dynamics. Telecommunications infrastructure requires not just research excellence, but the capacity to translate designs into physical equipment at scale. China had spent the previous 2 decades building the world's most comprehensive electronics manufacturing ecosystem, with specialized suppliers, component manufacturers, and testing facilities concentrated in industrial regions where telecommunications companies could iterate designs rapidly and scale production efficiently. Huawei could develop prototype 6G base stations, test them in integrated facilities, identify technical issues, redesign components, and return to production in cycles measured in weeks. American companies attempting similar development faced supply chains across multiple continents, relied on foreign component suppliers, and lacked the vertical integration that enables rapid iteration. The time required to move from research breakthrough to deployed infrastructure was structurally longer, the costs structurally higher, and the organizational complexities structurally greater for companies operating outside the Chinese manufacturing ecosystem. These advantages manifested not through sudden innovation but through patient accumulation. Each generation of telecommunications technology built upon lessons, capabilities, and institutional relationships established during previous cycles. Chinese companies that manufactured 3G equipment gained expertise that informed 4G development. 4G deployment experience shaped 5G engineering decisions. 5G implementation provided the testing environment for 6G research concepts. The learning curve was cumulative, and the institutional structure ensured that knowledge gained during each cycle informed the next rather than dissipating when individual researchers changed employers or funding priorities shifted. American telecommunications companies experienced greater disruption across technology generations, with mergers, restructuring, and strategic pivots, creating discontinuities that interrupted institutional learning. The result was not that Chinese engineers were individually more capable, but that the organizational systems supporting their work enabled more effective knowledge accumulation over time. The misconception that dominated Western discourse about Chinese telecommunications treated companies like Huawei as security threats requiring containment rather than industrial competitors whose capabilities reflected decades of coordinated development. This framing obscured the structural factors driving Chinese advancement and created the illusion that security restrictions could substitute for capability development. If Huawei posed risks because of potential Chinese government influence, the logical response was to exclude Huawei equipment. But this approach addressed symptoms rather than causes. The underlying reality was that China had built superior institutional capacity for coordinating long-term research, translating technical breakthroughs into international standards, and manufacturing telecommunications equipment at scale. Excluding Chinese companies from specific markets did not diminish this capacity. It simply seeded those markets, while Chinese firms continued advancing their technical positioning, patent portfolios, and standards influence. The strategic implications extend far beyond telecommunications equipment sales. 6G networks will provide the infrastructure foundation for technologies that define economic competitiveness and national security capabilities in the 2030s and beyond. Autonomous vehicles require ultra-low latency and high reliability that only next-generation wireless can provide. Industrial automation depends on real-time sensor networks, connecting millions of devices. Artificial intelligence systems need the bandwidth and computing distribution that 6G architecture enables. Military capabilities increasingly rely on networked sensors, autonomous platforms, and distributed decision-making systems that require advanced telecommunications infrastructure. The nation that controls the technical standards defining how these systems communicate gains structural advantages across every sector that depends on wireless connectivity. Standards-setting influence allows shaping specifications toward domestic technical strengths, ensures compatibility with nationally developed technologies, and creates opportunities for market access leverage in international negotiations. China recognized these strategic implications and structured its institutional response accordingly. The research programs initiated in 2017 and 2018 aimed not at winning a technology race, but at positioning China to define the terms on which the race would be run. Patents filed years before standards were formalized ensured Chinese companies would hold essential positions when specifications were negotiated. Manufacturing capacity built during 5G deployment could scale rapidly once 6G standards matured. University programs training engineers in relevant technical domains created the human capital pipeline required for sustained implementation, and coordination mechanisms linking research institutions, telecommunications companies, and government agencies ensured that progress in each domain reinforced the others rather than pursuing contradictory objectives. The system was designed to deliver compounding advantages over time, accepting short-term inefficiencies and investments that would not generate immediate returns in exchange for structural positioning that becomes increasingly difficult to challenge as it matures. The United States now faces the consequences of institutional structures optimized for different objectives. American telecommunications companies remain globally competitive in network operations, software innovation, and service delivery. But the capacity to manufacture telecommunications equipment at scale has atrophied through decades of offshoring. The political system struggles to sustain multi-year industrial policy programs, requiring patient capital and tolerance for early-stage losses. Universities produce world-class research but lack the coordinated funding and industry integration that translates academic breakthroughs into standards influence and commercial deployment. And the national security framing that continues to dominate policy discourse provides political cover for reactive measures while offering little foundation for the proactive capability development required to compete in domains where China has achieved structural advantages. The trajectory is not irreversible, but reversal requires recognizing what actually drives outcomes in complex infrastructure domains. Security restrictions alone cannot substitute for manufacturing capacity. Rhetoric about technological superiority cannot replace the patient work of patent filing, standards, participation, and ecosystem development. And political attention cycles, measured in months or years, cannot generate the institutional staying power required to compete against systems that measure progress in decades. The question facing American policymakers is not whether Chinese telecommunications capabilities pose risks. The question is whether the United States can build institutional structures capable of sustained coordination, long-term investment, and tolerance for the inefficiency inherent in early-stage technology development. Without such structures, the 6G era will simply extend patterns established during the 5G transition. Chinese companies advancing their technical positioning, expanding their standards influence, and deepening their manufacturing ecosystems while American policy debates remain focused on security threats rather than capability development. The infrastructure of future connectivity is being defined now in research centers, patent offices, and standards bodies by institutions that understand advantage compounds over time and that controlling the architecture of systems matters more than winning individual product competitions. That understanding and the institutional capacity to act on it across decades represents the actual strategic gap that security restrictions cannot close.